network where we train by flowing.
I'm going to be talking about some of the work that I've been doing with some of my collaborators at Argonne on this general kind of theme of training machine learning models for sampling and lattice gauge theories and so forth. So our motivation is, at the end of the day, we want to calculate these these observables, which are expressed as these high dimensional integrals that are computationally expensive to evaluate. And so the basic process, and I'm sure many of you are familiar with, is that we can approximate this integral using a sum over independent configurations and look at statistical quantities about a collection of configurations. In the case where each configuration is truly independent, we end up with the variance scaling like 1 over n, as you would expect. Unfortunately, as we know, in the real world, we have to deal with autocorrelations, and this has the effect of rescaling the variance in our error estimates for some observable O. The problem with this, obviously, is that this integrated autocorrelation time, which is a measure of how long we have to wait before our configurations are statistically uncorrelated, is that it's known to scale exponentially. So this is obviously a problem, especially as we continue to approach physical lattice spacings and smaller and smaller lattice. Yes, physical lattice spacings with smaller and smaller lattice spacings, or infinite volume limit. In particular, for lattice QCD, one of the major problems is that we have this phenomenon of topological freezing. And so this is the effect where the topological charge, this integer valued topological charge, QZ, tends to get stuck in sectors of fixed gauge topology. And so this can be seen by the charge remaining fixed for large durations of the simulation. And obviously, when we are stuck in some fixed sector, we're not actively sampling the entire target distribution, which is what causes these integrated autocorrelation times to diverge. So there's obviously a lot of work in this, or there's been a lot of work recently in this area, and there have been a lot of new developments in machine learning and just general computational algorithms that have started to kind of alleviate this and figure out what are some clever ways of getting around it. But at the moment, it's still a major problem. This can also kind of be seen by looking at how this quantity, the topological charge, evolves over the course of a Monte Carlo simulation at different values of beta. So you can see in this figure here on the right, starting from, say, beta 2, which is just the inverse coupling constant. The topological charge, you can see, is able to jump around pretty freely and samples from different sectors fairly well. Sorry, reminding me I had a talk to give in case I'd forgotten. And so anyway, yes, you can see at small values of beta, the topological charge is able to move around pretty freely. And as we kind of slowly ramp it up, you can see that it becomes more and more stuck. And finally, once we get to beta 7, you can see that it doesn't move around at all. So this is kind of the motivating factor. We want to encourage this tunneling that we see at small values of beta and basically find a way to continue this behavior up for smaller lattice spacings. In this case, we can define this quantity called the tunneling rate, which is basically just the absolute value of the difference in the topological charge between subsequent configurations. And so this phenomenon, this critical slowing down, is equivalent to saying that this tunneling rate goes to 0 as beta goes to infinity. So our goal then is to be able to draw independent samples from some target distribution, which can generally be expressed as the exponential of some action multiplied by this coupling constant. The way that this is typically done currently is using what's called Hamiltonian Monte Carlo, again, which I'm sure a lot of you are familiar with. The basic idea behind, so I'll go and give a little bit of background on this just because it's relevant for the approach that I'm going to describe. So you begin by introducing this momentum V, which is randomly distributed independently of the variable of interest. In this case, we denote it by X. The joint target density for the combined XV system is given by the product of their individual distributions. Explicitly is just still this minus exponential of the action and the minus just generic exponential of the kinetic energy, since it's normally distributed. And by doing this, by kind of introducing the momentum, that allows us to rewrite, or that allows us to evolve the dynamics of the joint system deterministically along isoprobability contours, which are characterized by constant values of the Hamiltonian. So these are just equipotentials. And we integrate along some trajectory from some initial state to some proposal state, with denoted by these little stars. So again, yeah, our goal is to integrate. Now our goal is to integrate Hamilton's equations along the trajectory. So what this looks like in steps is we start from our initial position, resample the momentum, and construct this initial state, which we denote by the shorthand curly C. Yeah, C. Nobody knows how to pronounce it. I've heard it a million ways. Anyway, we integrate our initial configuration along this trajectory using Hamilton's equations, starting from our initial configuration iteratively through the trajectory until we obtain this final proposal configuration. Once we've obtained this proposal configuration at the end of the trajectory, we can then either accept or reject it with probability determined from the Metropolis Hastings accept, reject proposal. And the idea, really the main idea, is that we can update our any of the variables using information about the complementary subset. And so this allows us to then have a deterministic way for generating new configurations that's not just random walk behavior, guess and check. What this looks like kind of pictorially is we have some target distribution we want to sample from. In this example, it's just a one-dimensional distribution. We augment this phase space with this, we augment the space of the probability distribution with this momentum, which lifts it into a D+1 dimension. And you can think of it as kind of being this process where we start from some initial state, we introduce this randomly sampled momenta, evolve it along a trajectory using leapfrog to some final state, which is then either accepted or rejected, and then we project away the momentum and obtain at the end of the day this new proposed configuration. And this process basically just repeats over and over again. And the idea is that this will eventually asymptotically converge in the limit to the target distribution given certain theoretical guarantees and stuff like that. So you can maybe see this a little more illustratively if you look at this animated plot here. And the idea is basically you just start, as you saw before, just from some place, integrate, and you either accept it or reject it. Kind of a nice little demo, but that later. So some of the issues with normal Hamiltonian Monte Carlo is that the energy levels are selected randomly, which can lead to slow mixing. It notoriously has difficulty traversing low density zones. So in the case of a distribution which is multimodal, and for this example, just a simple two-dimensional Gaussian mixture model, you can see that even for different values of step sizes, so that's this epsilon is step size is 0.5 on the left and 0.25 here on the right. It has difficulty traversing this low density zone between the two modes. And because of this, the configurations generally tend to end up fixed in one of the two modes and and is kind of unable to efficiently explore the entirety of the target distribution. So there are some kind of very involved, complicated schemes that have been proposed that can get around these types of things, but they tend to be specific to the target distribution and aren't very general. And so this serves as some motivation for what we would want in a good sampler, or what we might say are a list of desirable quantities. So first we want it to mix fast, quickly. And that's the idea that from some initial configuration, we're able to move away from it fairly quickly, in the sense that we don't have to take multiple steps before we obtain an independent configuration. Also, we'd ideally like it to quickly converge to the true target distribution. So there's this issue where HMC is asymptotically guaranteed to converge, but that might be, in practice, that might be a long time to wait. And so this is also a potential problem. And we would also like it to have the ability to mix across energy levels in isolated mode. So we would like to encourage it to, in this case, maybe take large steps or move away quickly from where it was previously. How we can do this. So the main idea for this approach is that we can generalize HMC by introducing these auxiliary functions denoted S, T, and Q. One set we introduce for the momentum updates, which we denote collectively, or for the position X updates, which we denote collectively by this capital lambda, and another identical set for the momentum updates, which are denoted collectively by this capital gamma. And as I'll show on the next slide, we just kind of introduce these equations or these functions into the leapfrog update in such a way that we preserve all of the necessary conditions for asymptotic guarantees. So as I mentioned, each of these functions are just kind of, at the moment, arbitrary functions that preserve the dimensionality of the target distribution. So that's an important point. And for now, they're just generic continuous functions, but in practice, they're implemented by neural networks, which are parameterized by some collective set of weights theta. The general architecture that this is based on is this real non-volume preserving flows, which uses these affine coupling layers that the previous talk Thomas, I think, had mentioned and was talking about, and has been kind of discussed at length here and within the kind of lattice generative modeling community more recently. And so in this approach, there are some kind of things we need to make sure that we maintain in order to ensure that the asymptotic convergence of HMC is preserved. So in particular, we need the system to be reversible, or we need the update method to be reversible. Also needs to satisfy detailed balance for some transition kernel K, and it needs to be ergodic. So ergodicity is a bit of a tougher one to check and test in practice, but nevertheless, yeah, it's still an important feature. So how this is actually done. So we can generalize this leapfrog update, which we call this L2HMC, it's based on previous work, but it's called this L2HMC update. And it maps the initial configuration, the C sub K, to some new proposal configuration denoted by this double prime. And how this works in practice is, so as in HMC, we first update the momentum, taking a half step, basically. Then we follow that by updating half of the coordinates of X. So we do this by introducing this mask M and its complement M bar. First, we pass the subset of X, which is determined by this mask M bar, through this collective series of updates, capital lambda, and add to it the unmodified components of X, followed by a complementary update of the, or followed by a subsequent update of the complementary component. So first we update 1/2 of X, followed by a complementary update of the other components of X. And finally, using this new X value, this X double prime, we then use that again to update the momentum in this final half step. So you can see this kind of pictorially here on the right. So we have in this top box, the X update, which you can see gets split into this first subset M bar and this complementary subset M. First one gets passed through this series of updates, capital lambda. That is then added to the complementary subset and so on. And so this kind of, as we saw before, this alternating pattern can be used to update complementary subsets and also importantly preserve reversibility. So because each of these updates are split and we have these masks kind of saved or known, we can run everything backwards and preserve and basically ensure that it's reversible. And on the bottom here, it's the same idea, but we have this momentum update. First gets passed through this collective series of updates, capital gamma, and then gets passed through and so on. And so if you look at and compare the L2HMC with the HMC update, you can see that they're similar, with the main difference being that we now split this middle step up into 2 complementary steps. Kind of a high-level overview for how this procedure works, or for how this training procedure works. So we start from at the very beginning, we start from some initial configuration X, draw our momentum, use that to update, or use that to update the momentum. This is then fed into the first X update. Obviously, it goes through, proceeds through the rest of the updates. We end up with some new proposal configuration. Using this proposal configuration, we can compute our loss function, which depends only on the initial and proposal configurations. Using the value from this loss function, we can then calculate the gradients with respect to the weights in our neural network theta. Then once we have those gradients, backpropagate them and update our weights through the network. And then we basically then continue on with either accepting or rejecting the proposal configuration. In the case that it's accepted, we use that new configuration and go back and basically repeat. If it's rejected, then we just more or less run the same procedure over again until we get a new configuration. So explicitly what this looks like, we additionally introduce this direction variable, which we denote by D, that's drawn from this uniform distribution of over 0 to 1, basically, that determines the direction of our update. So this is a bit of a subtlety, but we actually there actually need to be different update equations depending on the forward and backward direction. That's a bit of a technicality that the details aren't worth getting into for the sake of complicating things. So really, we just introduced this additional variable that is distributed independently of both my position and my momentum. And that allows us to write this joint target distribution again. It's just the product of the individual target distributions. And the idea is that this direction is resampled at the beginning of each trajectory. So before we begin the trajectory, we first pick up a direction that will be persistent. So in this example, we look at the forward direction, but the equations for the backward update are analogous. And so once we have this direction, we've determined if we're forward or backward direction. We construct our initial configuration as we saw before, pass it through what we call this leapfrog layer, which basically takes as input some configuration and returns this primed or proposal configuration. What this looks like explicitly, so for the forward momentum update, we have here this V double prime is the output value from this capital gamma. what this looks like is this first term, which is a momentum scaling, basically rescales the momentum by this exponential of the step size multiplied by this lowercase s sub v, which is one of these neural network functions. The second term, we've got this force scaling effect, which again is just some element-wise multiplication of this exponential of this function q, multiplying my force or the gradient of the potential of the action. And then this final term is just an effective translation, which helps to shift things around a little bit. Here we've also introduced this shorthand notation zeta, which is used to represent the inputs to the different neural network functions. And so it's important maybe to point out that each of these S, Q, and T neural network functions are used to update some variable. In this case, we're looking at updating the momentum. And importantly, then this function can't depend on and obviously can't depend on the variable to be updated. So in this case, we're updating momentum, and our network functions can then obviously only can take as input the position and the gradient of the action, which is the force. For the position update, we have kind of a similar description here. So we've got this first term, which helps to rescale the position. This second term, which now is rescaling the momentum instead of the force, as well as this overall translation factor at the end. Just so you can, just to make things a little bit clearer, you can see everything here. So this generalized leapfrog update begins with this momentum update, explicitly is given by this expression here with these three terms, followed by the position update, which again is given here by these three terms. But yeah, and so on and so on. I think that's all I have to say about that. So to build some kind of intuition for how this procedure works, or motivate kind of the inspiration for how this can be applied to these problems in lattice gauge theory. So it's simple to first consider a two-dimensional Gaussian mixture model. So we have, as we kind of saw before, these two normal distributions separated in space. And as you can see, HMC typically has trouble traversing this low density zone between the two modes and ends up being stuck in some localized region. And we can we want to avoid this behavior, right? So the goal is to train our sampler in such a way that it moves around effectively and prevent it from getting stuck basically in some localized region. So how we can do this is to maximize what's called this expected squared jump distance, which here is denoted by this expectation value of the acceptance probability times being multiplied by the Euclidean distance, or just the jump distance between this initial and proposal configurations. So multiplying this quantity delta by the acceptance value gives us an average quantity, and then summing and dividing by the total number of configurations in our batch or in our buffer gives us then a scalar valued loss function, which we can then evaluate the gradients for. And as you can see, so this is now showing samples generated from both the trained L2 HMC sampler here on the top, as well as two different runs for HMC. So on the top here, you can see this trained model is able to kind of effectively tunnel back and forth between the two modes and effectively sample the entire target distribution. Whereas, as we saw before, this HMC tends to remain stuck. And so this is just a kind of simple example, but this serves as some motivation for what we would like to happen and how we want to develop this kind of ideas for lattice gauge theory. Just for completeness sake, I suppose, I've included here a complete overview of the training algorithm and everything that's needed to kind of complete this idea. So we need some loss function, which, as we saw in the case of that Euclidean example, can just be the product of the acceptance probability and the Euclidean distance between initial and proposal configurations, some batch of initial states X, or equivalently your the prior distribution that you would like to sample from, doesn't matter either way. Some learning rate schedule that's used to update the network weights. This annealing schedule, which I think is on the next slide, that I'll explain a little bit more detail. And obviously the target distribution that we would like to sample from. So we begin by initializing the weights of our network and then enter this kind of first overall training loop. For each individual training step, we begin by resampling our momentum and resampling our direction. Once those have been established, we can construct our initial configuration. This initial configuration is then passed sequentially through n leapfrog layers. Each leapfrog layer basically transforming the input to this output primed configuration. At the end of the trajectory, we then compute this acceptance probability, which is given by this expression here, which is, as I'm sure most of you are probably familiar with, is generally equal to the ratio of the probabilities of the proposal and initial configurations multiplied by this Jacobian factor, which in the case of HMC is just equal to 1, and so is typically ignored. Once we've computed this acceptance probability, we can use that to then evaluate our loss function. Once we've obtained this loss, then we can evaluate the gradient and use that to update the weights in our network. Once we've done this back propagation step, we can then assign the next state in our chain to be either the proposal configuration if it's accepted, or the previous configuration if it's rejected. So as I said, as I mentioned previously, I forgot I hadn't talked about this annealing schedule. And the idea behind this is that we can introduce this scaling factor in the exponential during the training phase. So for each training step, we have this annealing factor, which are just arranged in order from the smallest value first and the final value last. One thing that's important is that at the end of training, so when we go to actually run inference and use these trained models, we need to evaluate it with this annealing factor being equal to 1 to recover the actual true target distribution. But otherwise, we're free to kind of vary these during training. The typical construction for this is we start from some initial value of gamma. In the case of lattice gauge theory, we could have the final value of gamma, or the final value being the physical inverse coupling constant that we want to sample at. And this would be, the initial value would be some arbitrary value smaller than that. Ideally, we want these to change by a very small amount during training. So in the limit of an infinitely long annealing schedule where these kind of change adiabatically, then that's ideal behavior, and we can actually, there's some asymptotic guarantees, but that's obviously completely unavoidable or completely unrealistic in practice. But the effect basically is that with this annealing factor being less than 1, it helps to rescale or shrink the energy barriers between isolated modes. And so by introducing this during the training, it helps at least from my interpretation, from what I can gather, it seems to help at the beginning of training where it's able to move around effectively. And as this kind of ramps up during the training, this behavior gets kind of baked into the network weights. In doing this, it allows the sampler to explore regions of the phase space that might have been previously inaccessible. And yeah, so here you can just see what effect this has and how it's actually included in the target distribution. So on to the lattice information or lattice material. So as I'm sure many of you know, for this so we'll be looking at the case of a two-dimensional U1 model. In this case, we have these link variables, which are just complex numbers that exist in this U1 space. These can be expressed in terms of the phase angles, which are the variables we're interested in and are referred to as x mu. These phase angles live in -pi to pi. In terms of these link variables, we can write the standard Wilson gauge action in terms of this plaquette x sub p, which is just the sum of each of the links around this 1x1 square. One other kind of physical quantity of interest is this topological charge, which, as we saw many slides ago, serves as a indicator of our sampler's performance. So this is something that we want to be able to generate independent configurations of. But as we saw, this has a tendency to get stuck at fixed values, especially as we go to larger and larger lattice volumes. So the typical definition of this topological charge, the one that's usually or more commonly referenced and used, is probably this Q sub z, which is the integer value topological charge, and is just basically the argument of the complex link variable. This has the kind of downside of being discrete and is not very hard to work with. But alternatively, we can kind of approximate this projection here in what would be the argument of the link variable with this sign approximation. And this has the advantage of being continuously differentiable and serves as a fairly close approximation. So it has a lot of the same qualitative behavior as the integer topological charge, but has the advantage of being continuous. This quantity is what's going to kind of be the important part of our loss function. So similarly to what we saw for the Euclidean example, we have a loss function, which is given by this expectation value of some metric squared being multiplied by the acceptance probability. In this case, now we've replaced the standard Euclidean distance with this real valued topological charge difference, which we call this tunneling rate, and is essentially just equal to the topological charge configuration of the proposal or the topological charge of the proposal configuration minus the topological charge of the initial configuration squared. This quantity multiplied by the acceptance probability averaged over a collection of chains then gives this expected value, which we can then obviously calculate gradients of and use for backpropagation. One kind of subtle difference between this and the L2HMC approach is that now we have to explicitly account for this Jacobian factor here in the acceptance probability. But as we saw previously, and as I'm sure has been discussed in some depth, by using these sort of affine coupling layers, we are able to ensure that this Jacobian factor is upper or lower triangular and efficiently computable. So some results you can see here on the top, we have a plot showing a comparison of the integrated autocorrelation time of the standard integer valued topological charge. So this is the actual physical quantity that we're generally interested in. Even though we use the real valued charge for training, when we actually run the sampler and perform inference, we are interested in this QZ, which is the physical quantity of interest. And we can look at then the integrated autocorrelation time of this quantity and compare it to HMC versus the trained model. So you can see across this range of beta values from 2 to 7, we see that HMC kind of scales it grows exponentially as we would expect and is kind of well known, versus for the trained model, while there is obviously still some growth with beta, it's significantly reduced and clearly orders of magnitude better than just kind of generic HMC. So you can look at this kind of explicitly, or you can see this explicitly if you look at the topological charge versus molecular dynamic time units, the MC stuff. So the HMC model here in black, again, we see remains stuck for large durations of the simulation, whereas the trained model is able to kind of effectively jump back and forth between different values. So just to kind of go in maybe a little bit more detail about some of the work that is ongoing and still that we're trying to figure out to try to better understand things like scaling properties and trade-offs between computational performance and cost. We can look at this plot here. So this is, again, the same plot that we saw before, the integrated autocorrelation time, but now we're looking at it, we look at the integrated autocorrelation time versus the versus molecular dynamic time units. Each of the axes are rescaled by the total number of leapfrog steps. And this is done basically to account for the additional cost introduced by having a longer trajectory. So with more leapfrog steps, we have more neural network weights and basically more computational requirements. But it, as we can kind of see here, it has the effect of being a little bit more robust, or is able to perform a little bit better. And so this is obviously just the kind of a trade-off. So you can, running with 5 leapfrog steps is noticeably faster than running with 15. But from this kind of picture here, it seems like the trade-off is ultimately generally tends to be worth it. So this is kind of a hodgepodge of different results, but the general trend, you can see that we're able to further reduce the integrated autocorrelation time by extending the length of the trajectory. So there's some kind of discrepancies here, but generally you see that as we go down, as the integrated autocorrelation time goes down, we have longer trajectories, with the best example being here, this case with 15 leapfrog steps. So I think that's all I really want to say. Really just that this is kind of an ongoing work in progress to figure out what's the best trade-off between the total number of leapfrog steps and the computational cost. One other kind of quantity that's a little bit, or helps to see what's going on here, is we can look at how the how the action behaves during the course of a single trajectory. So here on the y-axis, we have the, this should actually just be the average value of the plaquette versus leapfrog step. So at the beginning of the trajectory, leapfrog step 0, we have whatever the expected value of the plaquette is. So it's, for here, we have multiple different values of beta indicated by this color. But for beta equals 7, the infinite volume limit gives that the expected value of the plaquette should be whatever it is here, 0.9 something. And at the beginning of the trajectory, we can see that we're right on it exactly. And as the trajectory progresses, the trained model has the effect of basically reducing the value of beta, or analogously artificially increasing the energy. So the effect is that basically it gets fixed, clamped at the two endpoints, but during the middle of the trajectory, the trained sampler learns to artificially increase this energy during the first half before kind of going back down to its original value. And this has the effect of allowing the configurations to move about sort of in the middle of the trajectory, but then going back to the required value in order to kind of maintain these asymptotic guarantees. And so you can see this for across the different values of beta, so 7, 6, 5, 4. Each of these dotted lines represent the infinite volume, or the expected value in the infinite volume limit of the plaquette at that value of beta. And we can see here for beta at beta equals 7, the sampler is able to artificially increase the energy down to below what would typically be the energy for HMC at beta equals 3. So this kind of serves as an indicator of how well the sampler does. And so obviously we want to increase the energy as much as possible. And that's what we kind of optimize for during the training. You can see this. It's kind of another way of looking at these plots here. So on the left, this is another illustration of this plaquette value as it evolves over the course of a single trajectory. In the middle here is the evolution of this real valued topological charge. And finally, the effective action, which is just the total energy minus this log Jacobian factor. I'm running out of time. I think this is about it anyway. But yeah, again, this is actually just more or less the same plot, just maybe you can see it a little bit more clearly. Another one, different colors. Yeah, so I guess that's really about it. The implementation for all of this work here is available online. It's publicly available if anybody is interested and wants to hear more about it or look at it a bit more. Just actually recently, I finished this PyTorch implementation, and so that is now fully functional, but still has some work to be done. The TensorFlow implementation is much more highly optimized and evolved. Yeah, so I've been working on the TensorFlow implementation, was the first and has been around for quite a while now. But this new PyTorch implementation is now working and nice. And is a pretty, I would like to think, a generic interface. So this, while I've looked at it exclusively in the context of lattice gauge theory here, this kind of library is pretty easily extensible and has a generic interface. So you can pretty much just define an arbitrary action or probability distribution and pass it as an input and specify your loss function however you want, and it'll kind of automatically take care of the details, the behind the scenes work for you, so to speak. So if anybody is actually really is interested in looking at it, it's pretty easy to get up and running. Runs on CPU, GPU, whatever the case may be. There's ongoing work in progress to scale this up to 2D and 4D SU3, as well as the inclusion of fermions, which, as we know, will be a challenge, but the kind of roadmap for how we think we're going to do that has been established. I'll skip through this section, which isn't terribly relevant. Some acknowledgements, so people to say thank you to. So my collaborators are Young and James Osborne, both at Argonne. My PhD supervisor, Yannick, who I think is here. A bunch of other people that have been really instrumental in all of this development. Also these slides are available online. So yeah, I will send that somewhere, post it, GitHub, everything. So yeah, I think that's about it. That's all I had to say. So obviously, if there are any questions, I'll take them now.
Okay, thanks a lot for this nice talk. Yagio has the first question. He's coming.
Hi, Sam. Many thanks for the very nice talk. More than a question is an observation. I mean, the topological freezing is an important problem in lattice gauge theory, but is one of the symptoms, is not the reason of the freezing. So it's nice to cure the symptom, but this does not automatically mean that you have solved the problem. And this is for you, for me, for anyone else. I mean, this observation. I mean, there are other observables that could have long modes. And in fact, you cannot remove the long modes as you go to the continuum limit. You can mitigate. So the real question for which I don't have an answer is, okay, so this is one of the observables, and you can check that you do well on these observables, so you are on the right path. What would be a probe that the algorithm actually works better also for other modes that one would be interested in?
Yeah, so obviously, as you said, that's that's something that idea is something that I think you're completely right, and tends not to get too much discussion time because obviously it's not something people want to talk about. But it's challenging, right? So I've been working with Norman and Towu and these kind of collaborators that have been working on a variety of different techniques to deal with to try to help accelerate these long slow modes. So Zhao previously had looked at this idea of Fourier acceleration that seemed to do okay. But yeah, that's obviously a remaining challenge, and yeah, something that needs to be figured out. And I don't have the answer either, unfortunately. So
okay, thank you very much.
I see, Yannick, yeah, you have your hand up.
Yeah, your former supervisor has a question.
Yep. Yeah, very nice talk, Sam. Could you comment about the following fact? For the U1 model with a topological charge, you can calculate the topological susceptibility exactly, and you can estimate it by semi-classical method, and they agree pretty well. Have you checked that actually the learning preserve the original distribution and does not introduce a bias or
yeah, so I know, and I know that I think I remember we had talked about this at some point too. And I think I checked that at least for the first yes, because the which ultimately comes out in the susceptibility, right? Yep. And so I haven't included it here, but you can use that to basically get an expression in terms of an infinite sum for the susceptibility, and then compare HMC to L2 HMC and look at the susceptibility and see how well it agrees with this predicted value. Using the exactly this resummation approach, and I didn't include it here, but from what I can tell, it seems to agree pretty well, and so that's an indication that the distribution is preserved. I was going to say something else about that, but I don't remember that. Okay. Observables. In the case that were violated or there were some bias introduced, there's always an easy fix with this approach, right? So we can always just interweave some normal HMC steps. So in the case that our sampler does, for some reason, start to bias some observable, we can basically just run HMC for a while until we're back on it, take an L2 HMC step to move far, and then kind of repeat. And so that's like a kind of hacky fix, but something that might be usable or doable in the case that which it shouldn't be asymptotically. Everything is exactly guaranteed, but would be a possible fix. So.
Okay, thank you.
Okay, thanks. Tesh, a very quick question until
Oh,
we move on. I'll make it quick. Thanks, Sam, for the talk. I was just curious about the slide that you had on the number of leapfrog steps and the efficiency with increasing the number of steps. Was it the case that you sort of saturated at the gains made by steadily increasing the number of leapfrog steps, or could you have continued this? I mean, it looked like the maximum number had the lowest integrated autocorrelation time. So if you keep pushing it, would you get even more efficient results?
Yeah, so so we've gone up to, in practice, I think the largest I have results for is 20, but you kind of, so in this approach, one thing I didn't touch on or talk about is that what we actually do is use completely independent neural networks for each leapfrog step. So the first leapfrog step has its own complete neural network, second has its own complete neural network, and so on and so on. And this has the effect of basically improving the expressibility. So this allows for different leapfrog steps to learn different types of updates, but at the cost of being expensive memory wise, right? So that requires a lot of parameters and a lot of things to keep shared. And so in the case of more and more leapfrog steps in our trajectory, that has the effect of just eventually running into memory issues. And especially as we were to go to kind of scale this up. So you could get around that probably by sharing weights collectively for like neighboring leapfrog steps, which would help. And so then you could kind of continue to extend the length of the trajectory. But there does, and from what I've seen in our kind of limited looking at this, it does seem to eventually sort of level out. It does seem to plateau eventually.
Okay.
That might be due to either it's sampling and evaluating the charge as well as it can, or it might just be the limit of the expressibility of the networks. I mean, that still kind of remains to be seen.
But in this case, your memory bottleneck. Okay.
Yes, yeah,
Thank
exactly.
you.
Yep, no problem.
Okay, thanks a lot. Let's thanks Sam again.